I had a request to go over a few of the pre-lab questions and one of the post-lab questions. So that's what we're going to look at, 2 pre-lab questions and 1 post-lab question from the Michael Mo Rockets lab. First pre-lab question is, write a balanced equation for the single replacement reaction of zinc and hydrochloric acid to generate hydrogen gas. Now, this doesn't seem too hard. Okay, we know zinc and we know hydrochloric acid. Now, officially in Chapter 5 is when we learn how to name acids. But the idea is, you know that hydrogen gas was formed, and we know that that's diatomic. So if there's 2 H's there, there must be a 2 in front of the HCl. And we know zinc forms a Zn2 plus ion, chloride forms a -1 ion. So it's not too big a stretch to see that this is ZnCl2. But again, you'll get better at this in Chapter 5. Now, what's the total amount of hydrogen gas that could be produced in liters with 5 grams of zinc? So we're saying here that we've got 5 grams of zinc. And we're looking for what's the total volume. So desired is how many liters of hydrogen gas. Now this is a standard problem, and we'll say, okay, 5 grams of zinc. And I'm not going to do the problem, I'm just going to help you set it up. So we need grams of zinc and 1 mole of zinc. And we can see from the problem that for every 1 mole of zinc, we're going to get 1 mole of hydrogen. And we know that 1 mole of hydrogen is 22.4 liters of hydrogen. So we're using our molar volume, we're using the heart of the problem, and we're using the molar mass. So now you can just calculate the answer if you can read my writing. Next one says, write the balanced chemical equation for the yeast catalyzed decomposition of hydrogen peroxide, okay, to generate the oxygen gas. Now in this case, peroxide is H2O2, and what happens is the yeast is not a reactant or a product, so we actually write it over the arrow like this. So it doesn't get written in with the rest of the equation. And we are making water and oxygen gas. And we go back and say, okay, I've got 3 O's on one side, I got 2 O's on the other side. We're not going to start with the O's because they're in all 3 places. Let's start with the hydrogens. And we would say there's 2 hydrogens on the left, 2 hydrogens on the right. So that we can keep that 1 to 1. On the left there are 2 oxygens. Here we have 1 oxygen. So this must be 1 oxygen. So we can say 1/2 O2. In the same way, we could go back and double it, and we could say 2 turns into 2 H2O's plus O2. Both of those are correct. Now, what is the total amount of oxygen gas that can be produced if you begin with 15 grams of hydrogen peroxide? So, given is 15 grams of hydrogen peroxide. Okay, the desired is liters of oxygen gas. So we need to go grams for 1 mole of H2O2, and I'll leave you to calculate that. Then, heart of the problem, for every 2 moles of H2O2, we get 1 mole of O2. And then finally, if we want to go to liters, we know we're going to need to use our 22.4, the molar volume of a gas. And of course, for this whole thing, we are assuming that this is all at STP, or else we wouldn't be able to use 22.4. Now, we do learn way back in Chapter 12 or 13 how to deal with these kind of problems that are not at STP. But that's your basic setup, and those are the 2 pre-lab questions. Now, for the post-lab question, it's a little bit more complicated, but not difficult. And for this, there is a nice tool that we use called the icebox. And the icebox is we make a little chart down here just to kind of help us organize our information. And what happens is the first column here is the initial information, the initial amounts. And then the ending part here is our ending amounts. And then the middle part here is the change that we'd have to go through to get from the initial to the ending amounts. Let me erase this green, the red part. Now, up in the reaction, we're worried about the hydrogen amount, the amount of hydrogen here, worried about the amount of oxygen. We really don't care about the water, so that's why we have just X that out, because it's not part of our question. Now, let's try the one that's already written in, this guy right here, and we can see it says, if we started with 5 parts hydrogen, okay, and we can use these parts because of the fact that we know that every mole of a gas takes up 22.4 liters. So if we have equal volumes of gases, they have equal numbers of particles. So if we said we have 5 parts and 1 part, that means we have 5 times as much hydrogen as we have oxygen. Now, the change we're going to go through is we can kind of see, because it goes together in a 2-to-1 ratio, that all of the oxygen is going to be used up. Now, because this goes 1 to 2 ratio here, that affects this change column. So if 1 oxygen is used up, then 2 of the hydrogens are also used up. So we end up with 0 oxygen and 5 minus 2, 3 hydrogens. So we're going to have hydrogen left over, and there's 3 of them. That's where we get those numbers. So if we start with 5 to 1, okay, so that 5 to 1 here goes down to here, then we can see the oxygen is going to get used up, and the hydrogen will be a little bit left over. So we have excess hydrogen. And I'm going to erase all this red stuff. Now, let's go ahead and try our next one. And that is we have 6 and 0. So with the 6 and 0, well, this is kind of strange because if we have no oxygen, then obviously the change is going to be 0. So we're going to end up with 6 hydrogens, and that will be the excess hydrogen. So I'll erase this. Oops. And we'll say down here which is present in excess. The hydrogen is present in excess. How much is going to be left over? 6 is going to be left over. So that was actually kind of simple. Now, let's try the 4 and 2. So if I had 4 hydrogens and 2 oxygens. Well, again, let's just say that the oxygen is getting used up totally. So we use up both of those, would be 0. Now, since 1 is to 2, as 2 is to 4, then we can see that all of the hydrogen is going to get used up as well. So in this case here, there's going to be nothing left over. And so it would make sense to say there's nobody in excess. So let me erase my extra things here. And again, we'll say nothing is in excess and nothing is left over. So this is going to be the situation where we're going to get the maximum reaction because nothing's left over. Everybody gets used up. So 3 and 3, let's change colors. Now we can say, okay, since I need twice as much hydrogen as oxygen, we can kind of see that we're going to use up all of our hydrogen in this case. So we say 2 is to 1 as 3 is to 1.5. So we're going to use up 1.5, so left over we're going to have 1.5. So we have 1.5 left over, and that's going to be oxygen. So I'll erase. And we're going to say up here, oxygen is left over, and we're going to have 1.5 parts of that. Let's try the next one. 2 hydrogens and 4. Now again, you can see that the hydrogen is what's going to get all used up. And we say 2 is to 1 as 2 is to 1. So we'll have 3 left over. So we look at oxygen left over, and 3 of them are going to be left over. Oxygen, and 3 of them left over. Okay, 1 and 5. So we say again, the hydrogen is going to be used up. So 2 is to 1 as 1 is to 0.5. So what's left over? 4.5. So we're going to have oxygen left over, 4.5. And finally here we have 0 and 6. And we don't even have to do that because we know no reaction is going to happen. So we're going to have oxygen left over, and it's going to be 6. So you can see the situation is, this is the one place where there's nothing left over, so we should get the maximum reaction, and that is going to be our balanced equation. 4 is to 2 as 2 is to 1, so 2 is to 1. And the idea is this whole micromole rockets lab lets us balance an equation by doing an experiment. That's it.